Have you ever looked up at the sun and wondered where all that light and heat comes from? It's not a giant fire in the sky, not in the way we think of fire here on Earth. The sun is a massive, glowing ball of gas, and its incredible power comes from a process called nuclear fusion. It's the ultimate energy source, the engine that drives our solar system and makes life on our planet possible. For billions of years, the sun has been smashing tiny particles or atoms together in its core, releasing immense amounts of energy. It's a natural process that happens in every star you see twinkling in the night sky. It's beautiful, it's powerful, and it's something we humans are trying to bring down to Earth. Now, why would we want to do that? Well, think about how we get most of our energy today. We burn fossil fuels like coal, oil, and natural gas. This releases a lot of carbon dioxide into our atmosphere, which is changing our climate in ways that are frankly a bit scary. We need a new way to power our world, a clean way that doesn't harm our planet. That's where nuclear fusion comes in. If we can build machines that replicate the process happening inside the sun, we could have a nearly limitless source of clean energy. Fusion doesn't produce greenhouse gases, and its fuel comes from sources that are incredibly abundant. It would be a game changer for humanity, a way to power our cities and our future without polluting our home. The basic idea of fusion is pretty simple, even though making it happen is very, very difficult. It's all about bringing atomic nuclei, the tiny, dense centers of atoms, so close together that they overcome their natural tendency to push each other away. You see, these nuclei are all positively charged, and just like trying to push the north poles of two magnets together, they repel each other. To make them fuse, you need incredible heat and pressure, conditions like those found inside a star. When they finally merge, they form a new, slightly heavier nucleus, and in that process, a tiny bit of their mass is converted into a huge amount of energy. It's all explained by Einstein's famous equation, E equals mc squared. A little bit of mass can become a whole lot of energy. So scientists and engineers all over the world are working on building special machines called tokamaks and stellarators to create these star-like conditions. These devices use powerful magnetic fields to contain a super-hot, electrically charged gas called a plasma. We're talking temperatures hotter than the center of the sun, right here on Earth. The goal is to get the atoms in that plasma to fuse together reliably and efficiently, releasing more energy than we put in to get the reaction started. It's one of the greatest scientific challenges of our time, but the potential reward, clean, safe, and abundant energy for everyone, is what keeps us all so excited. Consider this. The fuel for a fusion power plant that could power a city for a day would fit in the back of a pickup truck. It's an amazing prospect. To cook up some fusion energy here on Earth, we need the right ingredients. The most promising recipe for the first generation of fusion power plants involves two special types of hydrogen atoms, which we call isotopes. Think of them as slightly different versions of the same element. The first ingredient is deuterium. A regular hydrogen atom has just one proton in its nucleus and nothing else. But deuterium has one proton and one neutron. This makes it a little bit heavier, which is why it's sometimes called heavy hydrogen. The great news about deuterium is that it's everywhere. About 1 out of every 6,000 hydrogen atoms in the water on our planet is a deuterium atom. So you can find it in every ocean, lake, river, and even in the water that comes out of your tap. We have enough deuterium in the world's oceans to power humanity for millions of years. The second ingredient is a bit more exotic. It's another hydrogen isotope called tritium. Tritium is even heavier than deuterium. Its nucleus contains one proton and two neutrons. When you heat a mixture of deuterium and tritium to over 100 million degrees Celsius, they have enough energy to overcome their repulsion and slam into each other. When they fuse, they produce two new things. One is a helium nucleus, which is a very stable and harmless particle. It's the same stuff we put in party balloons. The other product is a single high-energy neutron. This energetic neutron is key because its energy is what will ultimately capture to heat water, create steam, and turn a turbine to generate electricity, just like in a conventional power plant. So, why this specific recipe? Why deuterium and tritium, or DT as scientists call it? The reason is that this particular fusion reaction is the easiest one to achieve. The DT reaction can happen at lower temperatures and pressures compared to other potential fusion fuel combinations. Lower is a relative term, of course. We're still talking about temperatures 10 times hotter than the core of the sun. But in the world of fusion research, this is a huge advantage. It means the engineering challenge of building a reactor that can sustain the reaction is slightly less difficult. For the first wave of fusion power plants, making things as achievable as possible is the name of the game, and the DT reaction gives us the best shot at success. But here's the catch. The big problem that's causing a lot of concern in the fusion community. While deuterium is abundant and easy to get, tritium is the exact opposite. Tritium is radioactive, and it has a half-life of only about 12.3 years. This means that if you have a pile of tritium, half of it will decay into a form of helium in just over a decade. Because it disappears so quickly, there's virtually no natural supply of it on Earth. It's incredibly rare. This scarcity creates a massive challenge. We need tritium to get our fusion reactors started, but we can't just go out and mine it or extract it from seawater. This is the heart of the Tritium Trouble, a hidden crisis that we must solve if fusion energy is ever going to become a reality. Let's talk about just how rare tritium is. It's not an exaggeration to say it's one of the rarest substances on our planet. A tiny amount is created naturally in the upper atmosphere when cosmic rays, high-energy particles from space, smash into nitrogen atoms. But this process creates only a few kilograms of tritium spread across the entire globe at any given time, which is nowhere near enough for our energy needs. The vast majority of the world's tritium supply comes from a very specific and limited source, a special type of nuclear fission reactor called a CANDU reactor. These reactors, located primarily in Canada and Romania, produce a small amount of tritium as a byproduct of their normal operation. Currently, the total global inventory of tritium available for fusion research is estimated to be only around 20 to 25 kilograms. That's it, that's all we have. To put that in perspective, a single large-scale fusion power plant, once it's up and running, is expected to consume over 100 kilograms of tritium per year. The world's biggest fusion experiment, a project called ITER, which is being built in France, will use most of our current stockpile just for its initial experiments. As you can see, the math doesn't add up. We're on the verge of a serious fuel shortage before the first commercial fusion power plant has even been built. It's a classic chicken and egg problem. We need tritium to start fusion reactors, but the main way to get lots of tritium is from fusion reactors themselves. This shortage is becoming more urgent every day. The CANDU reactors that produce our current supply are aging. As these reactors are gradually decommissioned over the next few decades, our primary source of tritium will start to dry up. We are facing a future where the supply of tritium will shrink, just as the demand from the growing fusion industry is set to explode. This isn't a problem for the distant future, it's a problem for right now. The companies and research institutions designing the first fusion power plants are already factoring this supply crunch into their plans. They know that they can't rely on an external market for tritium because one won't exist. The solution must come from within the fusion reactor itself. The situation forces a critical realization upon the entire field of fusion energy. A future fusion power plant cannot be just an energy generator, it must also be a fuel factory. It has to produce at least as much tritium as it consumes, and ideally, a little bit extra to help start the next reactor. This concept is known as tritium breeding, and it is not just an optional feature or a nice-to-have upgrade. It is an absolute, non-negotiable requirement for fusion energy to be a viable, long-term solution for our planet. Without successful tritium breeding, fusion power will be limited to a few brief experiments before the fuel simply runs out. The dream of clean, limitless energy hinges on our ability to solve this fuel crisis. So, if we can't buy tritium, we have to make it ourselves. This is where the idea of tritium breeding comes into play. It's a clever bit of nuclear physics that happens inside the fusion reactor itself. Remember that when a deuterium and tritium atom fuse, they release a helium nucleus and a high-energy neutron. That neutron flies off, and ordinarily its energy would just be used to make heat. But we can make that neutron do double duty. The plan is to surround the fusion plasma chamber with a special blanket, a structure filled with a substance containing the element lithium. When one of those high-energy neutrons zipping out from the fusion reaction strikes the nucleus of a lithium atom, it can trigger another nuclear reaction. This neutron-lithium reaction is the magic behind tritium breeding. When a neutron hits a lithium atom, the lithium nucleus splits apart, and one of the things it produces is a brand new tritium atom. Voila! We've created our own fuel. In theory, for every one tritium atom we burn in the fusion reaction, the neutron it produces can go on to create at least one new tritium atom in the surrounding blanket. This would create a closed, self-sustaining fuel cycle. The reactor would consume tritium and lithium, and in return, it would produce energy and more tritium. It's an elegant solution that could solve the tritium scarcity problem for good, turning fusion into a truly sustainable energy source. However, moving from this elegant theory to a working, practical system is incredibly challenging. The goal is not just to replace the tritium you use, you need to make more than you consume. This is called achieving a tritium breeding ratio, or TBR, greater than 1. A TBR of 1.0 means you break even, but that's not good enough. Some tritium will be lost in the system, some won't be perfectly extracted from the blanket, and you need a surplus to fuel new power plants. Scientists estimate we need a TBR of at least 1.1 to be safe. This means that for every 10 tritium atoms burned, we need to produce 11 new ones. That extra 10% margin is very, very hard to achieve. The difficulty lies in the complex engineering of the breeding blanket. Not every neutron produced in the plasma will make it to the lithium. Some will be absorbed by the structural materials of the reactor wall. Some might just pass straight through the blanket without hitting a lithium atom. The blanket has to be designed with incredible precision, with openings for diagnostics, heating systems, and fuel injection, all of which create gaps where neutrons can escape. Furthermore, the blanket must operate in one of the most hostile environments imaginable: intense heat, extreme radiation, and powerful magnetic fields. Building a blanket that can effectively breed tritium while surviving these conditions for years on end is one of the toughest engineering hurdles in fusion energy. As if the tritium problem wasn't enough, our solution, breeding it from lithium, introduces another challenge. It turns out that not all lithium is created equal. Natural lithium, the kind you dig out of the ground or extract from brines, is made up of two different isotopes. The vast majority, about 92.5%, is an isotope called lithium-7. The remaining 7.5% is a much more useful isotope called lithium-6. While both isotopes can react with neutrons to produce tritium, lithium-6 is far, far better at it, especially with the lower energy neutrons that are more common inside a breeding blanket. To make tritium breeding efficient enough to reach that all-important breeding ratio of over 1.1, fusion reactors need lithium that has been enriched in lithium-6, meaning the percentage of lithium-6 has been artificially increased. This need for enriched lithium-6 creates a new supply chain bottleneck. The process of separating lithium-6 from the more common lithium-7 is difficult, energy-intensive, and expensive. For decades, the primary method involved a complex chemical exchange process using mercury, which is a highly toxic substance that poses significant environmental risks. Due to these risks, and a lack of demand, global production of enriched lithium-6 has been very limited for a long time. The world's existing supply is small, and much of it was produced many years ago for military purposes. Just like with tritium, we are facing a situation where the future demand from a global fusion industry will dwarf the current supply. To make matters more complicated, the fusion industry isn't the only one interested in lithium. You're probably holding some lithium right now in your phone or laptop. The global demand for lithium has skyrocketed due to the boom in electric vehicles and battery storage for renewable energy grids. While these industries primarily use natural lithium, the massive scale of their mining and processing operations affects the entire lithium market, influencing prices and availability. This creates competition for the raw lithium that would be needed as feedstock for enrichment plants. As we try to solve one clean energy challenge with fusion, we find ourselves competing for resources with other clean energy technologies. So, the successful rollout of fusion power depends not only on building reactors and breeding tritium, but also on creating a whole new industrial capability to produce large quantities of enriched lithium-6 safely and affordably. We need to scale up production from kilograms per year to hundreds of tons per year. This requires significant investment in new, cleaner enrichment technologies and the infrastructure to support them. Without a reliable and scalable supply of lithium-6, even the most perfectly designed breeding blanket won't be able to do its job, and the dream of a self-sustaining fusion fuel cycle will remain just out of reach. It's yet another critical piece of the fusion puzzle that we must solve. The good news is that scientists and engineers are not just sitting around worrying about these problems, they are actively working on solutions. The fusion community is tackling the tritium and lithium challenges with creativity and determination. On the tritium breeding front, researchers are designing and testing innovative new concepts for breeding blankets. These blankets are complex marvels of engineering, using different materials and configurations to maximize the chances of a neutron hitting a lithium atom. Some designs use a solid lithium compound like a ceramic pebble cooled by helium gas. Others use a liquid metal such as a lithium-lead mixture, which can act as both the breeder material and the coolant at the same time. These advanced blanket designs also incorporate materials called neutron multipliers. The most common one is beryllium. When a high-energy neutron from the fusion reaction strikes a beryllium nucleus, it can knock 2 or even 3 neutrons out. It's like getting a bonus. This single neutron effectively becomes multiple neutrons, which dramatically increases the probability of hitting a lithium atom and breeding tritium. By carefully layering lithium compounds and neutron multipliers, engineers can fine-tune the blanket to push the tritium breeding ratio above that critical 1.1 threshold. Experiments at facilities around the world are testing small-scale mock-ups of these blankets to see how they perform under realistic conditions and to validate our computer models. On the lithium side of the equation, the race is on to develop better and safer ways to enrich lithium-6. The old, mercury-based methods are simply not suitable for the scale or the environmental standards of the 21st century. One of the most promising new techniques is a process called ICOMAX, which stands for Ion Exchange-Based Chromatographic Mass Separation. This method uses a chemical process similar to what's used in water softeners, but on a much more sophisticated level, to separate the lithium isotopes without using toxic mercury. Other researchers are exploring techniques involving lasers or centrifuges. The goal is to find a method that is not only environmentally sound, but also efficient and economical enough to be scaled up to meet industrial demand. These efforts are a global collaboration, involving national laboratories, universities, and a growing number of private fusion companies. The urgency of the problem has spurred a wave of innovation. For example, some companies are designing compact fusion power plants that might require less tritium to start up, easing the initial fuel burden. Others are developing highly efficient systems for extracting the newly bred tritium from the blanket material, ensuring that as little of our precious fuel as possible is lost. Every improvement, whether in blanket design, lithium enrichment, or tritium extraction, brings us one step closer to a workable, self-sustaining fuel cycle and ultimately to a future powered by the clean energy of the stars. Given all the trouble with tritium, a logical question arises: do we really need it? What if we could get fusion to work using only deuterium, our abundant fuel from seawater? This is indeed a possibility, and it's a very attractive one. A fusion reaction using only deuterium, known as a DD reaction, would completely eliminate the need for tritium breeding and the complex supply chain for lithium-6. It would simplify reactor design and solve the fuel shortage problem in one fell swoop. In a DD reaction, 2 deuterium nuclei can fuse in a couple of different ways, sometimes producing a tritium atom and a proton, and other times producing a helium-3 nucleus and a neutron. However, as with most things that sound too good to be true, there's a significant catch. The DD fusion reaction is much harder to ignite and sustain than the DT reaction. It requires even more extreme conditions, temperatures that are roughly 5 to 10 times higher, and pressures that are significantly greater. Achieving these conditions and holding them steady is a far greater scientific and engineering challenge than what we're already facing with DT fusion. It would require more powerful heating systems and even stronger magnetic fields to confine the plasma. Essentially, we would be trying to solve a more difficult physics problem to avoid the tritium engineering problem. Despite these hurdles, the idea of deuterium-only fusion remains a compelling long-term goal. Some scientists envision a multi-stage approach to fusion energy. We could start with DT reactors to get the first generation of power plants online. These reactors, while requiring tritium breeding, would help us perfect the technology of controlling fusion plasmas. The tritium produced as a byproduct in some of the DD reactions could even be harvested and used to fuel other DT reactors. Then, as our technology advances and we become more skilled at managing fusion energy, we could transition to second-generation DD reactors, leaving the tritium challenges behind. This provides a potential pathway to an even cleaner and simpler form of fusion power in the future. Ultimately, whether we stick with DT fusion or eventually move to DD, overcoming our fuel challenges is absolutely essential. The path to fusion energy is not a single straight road, It's a complex journey of scientific discovery and engineering innovation. The Tritium Trouble has brought a critical issue to the forefront, reminding us that building a power source is about more than just the reactor itself. It's about the entire fuel cycle that supports it. By tackling the challenges of tritium breeding and lithium enrichment head-on today, we are paving the way for a future where we can finally harness the clean, abundant, and powerful energy of the stars to power our world for generations to come. It's a challenge worth undertaking,